Hi, my name is Aiden, and this is my video about our DC motor. So, why is it called a DC motor? DC stands for direct current, which means the current travels in one direction, as opposed to an alternating current, which switches directions periodically. For demonstration, if we take one wire and connect it to the positive end of a battery, and one to the other end, the negative end, we make it run. The motor is constantly dissipating energy when running, which is why the battery is needed as a power source. If we take apart this motor, we can identify some key elements. First of all, we have two magnets that create a north-south dipole for our motor. We also have coils of wire here, where positive charge flows and interacts with the magnetic field to move the motor. Further down, we have the commutators here and the brushes here, which alternate the direction of the current periodically through rotation. The direction of flow depends on the way you hook up your battery to the wires, as charge will flow from the positive end of the battery through the motor to the negative end. Charge represents the movement of positive particles, though the phenomenon is actually negative particles moving in the opposite direction. So I drew a diagram for the motor in a few parts. The first part shows the commutator brush action, where charge flows from the battery through the wire to the brush where it touches a commutator. Charge will go through this commutator to the coils and exit through the commutator or commutators that the other brush is touching, completing the flow through the battery. I've labeled the commutators A, B, and C for reference in the next diagram. In this diagram, we can see how charge flows through the coils. The positive charge is going through commutator A, so it splits out between these two coils and continues to commutator C, where the current exits through the other brush. Our final diagram shows the position of the two magnets and the direction of the magnetic field in relation to the coils, flowing from north to south. This field is necessary for the coils to move. We can use this diagram to think about the Lorentz force on the coil. The magnetic B field interacts with the charge moving through the coil to create a force based on the direction of the components. For instance, using the right-hand rule, at the top, if we do V right, cross B into the board, we experience a net force of up. If we put V parallel to the B field, as in into the board or out of the board, we experience no force, which we can see from the Lorentz equation. QVB sine theta, if we plug in 0 or 180 degrees for theta, which is the angle between V and the B field, then we'll get 0, so we'll experience a net force of 0. We can think about the motor in terms of poles trying to align because the coils generate their own magnetic fields by Ampere's law. This part shows a top view of the coil where we can apply the right-hand rule, and we show that the loop creates a force out of the page on the inside and into the page on the outside. This diagram shows how multiple coils stacked create a net force through the middle. We can then show positions with the most and least forces generated. The left diagram generates the most force because like repels like for magnets, and the right diagram generates the least force because of the same concept. The coil of wire rotates based on the Lorentz force. If the coil is fully encompassed in the B field, then there's 0 net force, a minimum. If the wire is partially off the magnet, there will be a net force on the coil because the coil experiences no force outside of the field, but will experience it in the field and therefore pull the coil in that direction. Maximum force would be when the coil is halfway in the field, experiencing as much force in one direction as possible. Say, for example, we move this coil. When it is on the right side, it experiences a net force left. As soon as it moves more than a third of the rotation, if we kept the same direction of the current, the Lorentz force would pull it back towards the center. This doesn't actually happen in the motor because the commutator brush system switches direction of the current V, so by the time the coil reaches the outside, the coil experiences a net force that pushes it away. The motor cannot work perpetually because of energy dissipation. First of all, the battery does not have infinite energy, so will eventually run out. Another source of loss is electromagnetic induction, which gives rise to eddy currents. Current running through the coil generates a B field, and when the coil moves, it creates a changing magnetic field and generates current in a conductor, in this case, the metal casing, consuming energy and creating unwanted heat. This is minimized by creating thin strips of insulated metal to prevent larger currents that would form in one solid piece of metal. That's about it for my video today. Thanks for watching. Hope you learned something.